Well, I'm going to continue with the mini course that Catherine already started. She gave us 2 lectures. In the first one, she gave loads of basic ergodic theory that we will use through the course. And in the second one, she talked about dimension theory, many results that we will need in what follows. What I will do today is to bring up another set of tools, namely thermodynamic formalism. But what I want to do is to concentrate in examples. I mean, I don't want to develop the theory too much. Actually, I want to develop it as little as possible. But to concentrate in examples where you can actually compute certain things and try to solve problems using these thermodynamic formalism tools so that you get a flavor more or less of what kind of things you can prove with it. Okay? So I will start like in a few minutes defining some basic facts. But I hope to go really fast to some concrete examples, some concrete dynamical systems, some concrete potential, so that we can compute the pressure and see what's going on there. So the setting I'm going to use is basically the same setting as Catherine has already established. So I'm going to consider a dynamical system, which is going to be a cookie-cutter map. Okay, so that's something like this. In the cases I'm going to consider today, everything's going to be linear, so even better. And I also need a potential, which is a function. That goes from x to r. Our dynamical system is somehow good, in the sense that it's uniformly hyperbolic and it has lots of good properties. In order to make things simpler, I will ask also the potential to behave well. One could eventually define the pressure for any continuous map, but I will ask better regularity properties here. So a Holder function. Actually, for what I'm going to do today, I only need this function to be piecewise constant in each of the pieces that define the cookie-cutter map. So I'm going to give you a first definition, which is one of the main objects in thermodynamic formalism. So the pressure of the function phi with respect to the system T is defined by the following limit. It's an ugly expression. I'll explain in a second what does it mean. Let me first say, though, that there are several ways of defining the pressure. This is by no means the most general one. In particular, require the dynamical system to have periodic orbits, and you could do it without that condition. But it's very well suited to the setting that we have, and any other definition in that setting coincides with the one I'm giving you here. So how do you make sense of this expression? The first thing that I would try is to consider the null potential. That is the map that's equal to 0 everywhere. Then what is the pressure of 0? pressure of 0 in that setting becomes the following. Okay? So basically what you're counting here is the exponential growth of periodic orbits. So if you want to put it in a loose way, it's something like this, right? You count the number of periodic orbits, and this grows more or less like n p of 0. Okay? We will call p of 0 the topological entropy of the map T. So it's a definition, if you like, that will be the topological entropy of T. So what does this expression mean then? You can think of it as some sort of weighted topological entropy. Because instead of counting the number of periodic orbits, which is basically what you have here in this term, what you do is to weight it with the function phi. Okay? So each point in the periodic orbit doesn't weight exactly the same, but you give it a specific way given by the function or the potential. So this idea of weighted entropy can be actually made more explicitly using showing the following theorem, which is one of the fundamental theorems in the field. This is called the variational principle. And it was proved in different degrees of generality, first by Ruel and later by Walters. It's like in the mid-70s, I think, a bit earlier. And what it says is, in the same setting that we are here, is that the pressure is nothing but the supremum of this expression here. I'll have to explain a couple of things here, but let me first say that this is the same as this. So M is the set of T invariant probability measures. And the set E is a subset of M, is the subset of M of ergodic invariant measures. Well, the set this term here is the entropy with respect to a measure. So I'm going to define it the following way, and only for ergodic measures. So if mu is an ergodic measure, then the following limit exists and is constant and here what I'm putting is the sets that Katrin defined, which are the cylinders that could shrink to a point. So I will call this the entropy of the measure. What's the idea? You pick up a measure, look at the system through that measure, And this number here, what it's telling you is how complicated the system looks like when you look it through that measure. For example, take an atomic measure. Take your atomic measure, look at the system through it, and what you see is nothing but a fixed point, for example. So the system is extremely simple. In that case, this number is 0. The entropy of an atomic measure supported at a fixed point is 0. If you consider the Bernoulli measure, which is uniformly distributed in each of the pieces of the cookie cutter, say you have m pieces, what you get here is 1 over m to the power of n. So the entropy of the Bernoulli measure, uniformly distributed, is nothing but log of m. Okay, so that's a rough idea of what is there. So what's the variational principle saying is that the pressure is nothing but some sort of weighted entropy. Okay? What's the problem one has to face when dealing with this type of systems? We have beautiful theorems when you have an ergodic measure that describes the dynamics of the system almost everywhere. You have Poincare recurrence, you have Birkhoff. You can say lots of things that happens almost everywhere. The problem is that this set here, it's huge. It's enormous. It's really enormous. Crowley already showed us that it was compact and convex. So it could be a point. But in this context, it's an enormous set. It's infinite dimensional, and it's actually very complicated. The extreme points are dense on the whole thing. So it's kind of thing that you cannot imagine very easily, because if you think of the extreme points of a convex set, these things will never be dense on the whole thing, but infinite dimensional spaces, you know, allow for counterintuitive things. So the problem is that it's massive. It's massive, and you have to have a technique to pick up relevant measures. Thermodynamic formalism can be thought of as a set of techniques that allow you to choose relevant measures within the set of invariant measures. And how do you do that? You do it in the following way. A measure mu in M is an equilibrium measure for the potential of the function phi if the pressure of phi is actually this, meaning a measure that attains this supremum. In the case of the null function, when you are considering 0 and you're looking at the entropy of T, a measure that attains that supremum is called measure of maximal entropy. Okay? So it's a measure that sees all the disorder, if you want, of the system. In this sense, equilibrium measures are somehow a generalization of these measures here. So that gives you a way to pick up measures. You might argue that the only thing I have done here is just to shift the problem. I didn't know how to choose measures within the space of invariant measures. And what I'm doing now is picking up a potential and then choosing a measure related to that potential. Therefore, what I've done is not much that changing the problem stated within measures to a problem stated within functions. You might be slightly right, but not completely. Not completely. I don't know if I will try to convince you about that, but, well, at least in the examples I'm going to show here, we choose a particular potential that will be suited to the problems that we want to tackle. Nevertheless, if you concede me that measures of maximal entropy are important, if you allow me not to convince you of that, then, in general, equilibrium measures are also important. And there is a small argument that I can give to anybody later if you want, but if you construct a suspension flow over a cookie cutter with a roof function phi, assuming that phi is positive, then the measure of maximal entropy of that flow will be nothing but the Lebesgue measure times an equilibrium measure for a suited version of this potential. So in a sense, if you don't want to allow equilibrium measures as a reasonable thing, you can think of them as measures of maximal entropy of a certain flow, if you want. If you don't, well, it doesn't matter. So the question of existence and uniqueness of equilibrium measures is at the core of the theory. I mean, that's one of the main things that you want to prove, and you want to consider, you want to study. And, well, from here you can see that there are several things you might want to have in order to ensure existence of equilibrium measures. For example, in our setting, this space is compact. So if you pick a sequence that goes and converges to this number, if the entropy map is aposemi-continuous, then any limit point will be an equilibrium state. So you might want to find conditions in order for the entropy map to be aposemi-continuous. It's not that easy, but at least in these examples that I'm dealing with, we do have that conditions. Therefore, we have equilibrium states for the potentials that we are studying. In general, you have somehow two things that play a part in the problem when you study. On the one hand, you have the system, and on the other hand, you have the potential. So if the system is good in the sense that it's hyperbolic or expanding or whatever good system you have, and the potential is regular enough, the thermodynamic formalism works in a nice way. You have uniqueness of equilibrium states, and the equilibrium states are well behaved, are interesting ergodic measures. But if you weaken any of these two, if your system is no longer uniformly hyperbolic, or if your potential is no longer regular enough, things go wrong. And you can get a totally different behavior. But I'm not going to talk about that. I'm just going to focus on this very well-behaved case of cookie cutters with very regular potentials. So what's the system I want to study? It was a system actually that Crelli already introduced in his previous lecture. And it's the following. I want to consider the base M representation of a number. So if you pick M, a natural number larger than 2, then any x in between 0 and 1 can be written in the following way. Which is the base M expansion. If you think of M10, you have just the decimal expansion. Okay, where all these digits belong to the set. Okay? So there is a natural dynamical system related to this expansion, which is the map, the interval map, mod x, mx mod 1. This has been discussed already, so I hope that you remember. So there is a dynamical system closely related to this expansion. And the map is, I'll probably drop the subscript m very soon, and this is mx mod 1. So if you, this is from the interval. Yeah. You can draw a picture of this. I'm going to draw it for M3. The way you draw these things is always the same. You just draw mx, and this is a line that goes like that, and then you cut it off with the integer parts. So it's a nice cookie-cutter map, full branched. Each of the slopes is constant. It's m. The length of each of these intervals is 1 over m. And it's related to this expansion. In the following, well, I already clearly explained what it is, so I'm going to go faster here. So maybe the main idea is that if you know the orbit, if you know the whole orbit of a point through the map T, then you know the expansion. And the idea, well, it's already been said, but I will repeat it, is the following. If Tn of x belongs to the following interval, so you're looking at which of these 3 intervals does the nth iterate of the map lies in, then you know that the digit an plus 1 is actually equal to k. So you follow the orbit, you look where is it going, and then you know the exact expansion that this number has. So then it's clear that if you study some ergodic properties of the map T, you will be able to say things about the statistics of the digits in its expansion. Okay? One remark is the following. The Lebesgue measure is T invariant and ergodic. Katrin already showed us how to prove these kind of things. And basically the idea is, in this example, you pick an interval of length n, look at the pre-images, and in this case, it's just, if this was length L, each of these has length L third, and there are 3 of them, so they have the same measure. The fact that it's ergodic is slightly harder, but it's part of the exercises. Okay, so we have the Lebesgue measure, which is ergodic. Then we can apply all these results that we have, Birkhoff and Poincaré, that have already been discussed here. So, remark, Poincaré recurrence theorem implies that Lebesgue almost every x in the interval is such that there exists a sequence for which, oh, I didn't fix that, well, okay. Such that there exists a sequence for which NA is equal to K, where K was fixed before between the digits. What I mean, the only thing I'm saying is, you know that if the orbit passes through here, then the digit K appears in the expansion. This set has positive Lebesgue measure. Therefore, every point that starts here returns infinitely often to this set, and that means that this digit appears infinitely often. If you start somewhere else, well, then you show it. But you will eventually pass through here, and then you repeat the argument, right? Yeah? Okay. So that's a first result that we obtained for Lebesgue almost every point. With Birkhoff, ergoic theorem, we can actually compute the frequency at which this happens. So let K be one of these digits, and then define x in 0, 1, and then you have that Tk of x will be the limit of the number of digits equal to k among the first n divided by n. Of course, this limit need not to exist, but if it exists, I will call it the frequency of the digit k in the expansion of x. So here we can remark that while this is a definition of a dynamical nature, because in the light of what we have discussed, this is the same number as the characteristic function of Km, K plus 1m, Tix. So you're counting the exact number of times that the orbit passes through this set. Okay? You look at the orbit, count how many times that it passes through the set K over m, K plus 1 over m, and that gives you exactly this number. This is Lebesgue almost everywhere, and this is because of Birkhoff theorem, equal to the Lebesgue measure, or the integral of this, which is the Lebesgue measure of K over m, K plus 1 over m, and it's 1 over m. Okay? So the frequency of every number is exactly the same, and it's 1 over m. Almost every number. Okay? Of course, there are plenty of numbers for which the frequency is different. For example, if you, I don't know, everybody can construct his favorite example, but if you have m equal to 2 and a point x which is just zeros, then the frequency of 0 of x is 1, while the frequency of 1 is 0. So what I want to do now is to study sets for which the frequency is not this one. It's not the one given by Lebesgue. And what I want to do is essentially to sketch a proof of a result by Besicovitch using thermodynamic formalism. Of course, Besicovitch did not need to use thermodynamic formalism, and probably his proof is much nicer than what I'm going to do here. But the way I'm going to prove it generalizes much better. You can actually tackle problems which are much harder that you cannot do using Besicovitch arguments. So the idea is the following. I'm going to concentrate in the case, from now on, let m be equal to 2, and alpha a number in between 0 and 1. And consider the set J alpha of all points in 0, 1, for which the frequency of 0 is equal to alpha, and the frequency of 1 is equal to 1 minus alpha. If alpha is 1/2, we know that that set has a Lebesgue measure equal to 1. And if alpha is not 1/2, then that set has measure equal to 0. So we have to estimate the size of this set using other means. And well, Katrin already defined house of dimension and explained us a lot of things about that. So we'll try to estimate what is the size of this set in terms of house of dimension. And the result is the following. The house of dimension of the set J of alpha is equal to over log 2. Okay? So I will try to give you an idea of how, using thermodynamic formalism, you can prove such a statement. I mean, there is a nice thing about this. Well, this is a 1, of course. Thank you. Yeah, of course. I mean, alpha log alpha, 1 minus alpha, log of 1 minus alpha. Sure. Now, otherwise, it would be funny. Okay. So let me keep it clear here so that there is no confusion. This is not 1 over log 2. There we are. Thank you. Okay. How can we prove this? This set is defined without explicitly using any dynamical system, and you could actually try to prove it without using it. But I'm going to try to estimate a number which is absolutely dynamical. I will try to consider the following. The supremum of the entropy of all measures that are supported in this set and are ergodic. Okay? Of course, this set looks even nastier than this one, but that's the approach we're going to follow. I would like to estimate this supremum. And in order to do so, I'm going to make use of thermodynamic formalism in the following way. And this is somehow the strategy that at some point at the end of her lecture, Katrin suggested. I mean, what you have to do in order to compute the size of dynamically defined subsets like this, well, sometimes works, sometimes it doesn't, but it's a strategy, is to look at all the dynamically defined measures supported on that set, and then to estimate the size of that measure. I could have replaced here, instead of entropy of a measure, the Hausdorff dimension of the measure. But I don't want to define more things, and in this case, I mean, the Lyapunov exponent is constant, so there's no need to do that. Okay? Well, no, whatever. I mean, this is what I want to estimate, and the strategy is pick up measures that are supported on that set and compute its size. If you maximize this, there's a good chance that you could actually estimate the size of this set. So how do we do that? We have the dynamical system, we need a potential. It's going to be log of alpha if x lies between 0 and 1/2, and log of 1 minus alpha if x lies in, well, 1/2 1. And what I can do now is to compute the pressure of the following function. I will define Pt from R to R, and to each parameter t, I will compute the pressure of t times this potential. So it's a one line that you follow. The good thing about this kind of system is that since everything is linear or piecewise constant in the element of the partitions, you actually can explicitly compute the entropy, the pressure. It turns out that Pt is log this is in the this is in the exercises, the exercise sheet that we have. It's not that hard. Huh? I mean, if you try to compute it using the definition, it should work. So you can picture this. Well, if alpha is different from 1/2, there is something special here if alpha is equal to 1/2, then this function is strictly decreasing real analytic and strictly convex. If alpha is equal to 1/2, then it's no longer strictly convex, and what you get is a straight line. So let's do a picture of this. You have t, you have pt here, and this is a curve that looks like this. It passes here through the x, through the yx in log 2, which turns out to be the topological entropy of a map with 2 full branches. It's what it should be. P of 0, I define it as the topological entropy. And here, it's 1. Okay? If you pick 1 here, then everything cancels out, and it's log of 1, which is 0. There are even more, actually, very good things about this. It is a good example in a sense because that shape of the pressure is what you normally get when things do behave very well. If you have a, well, the strictly decreasing part maybe not, but strictly convex and real analytic is something that happens when you have a uniformly hyperbolic system and a very regular potential. So in this sense, it's a it's a good example. It's a representative example. It's not something very strange coming from the fact that I've chosen very specific potentials, a very simple dynamical system. It's something that holds in more generality. Okay. It's until what time do I have? Okay. Yeah. Well, it turns out that there exists an equilibrium measure for every t times, for every potential t times phi alpha, but I will be interested only in the case of t equal 1. And that measure, it's a Bernoulli measure. Defined in the following way. In 0, 1/2, you put alpha, and in 1/2, 1, you put 1 minus alpha. I know that actually this is an equilibrium measure because I can compute, I know that the pressure is 0. I can compute the integral of phi with respect to this measure is alpha log alpha, the potential weighted log alpha in the first interval, and the measure is alpha. And the other one is 1 minus alpha log 1 minus alpha. It's locally constant, okay? So it's a sum. And moreover, one can compute the entropy of this measure okay, which is the number that actually appears in the numerator of the Besicovitch result. This can be computed also with the same formula. It's not complicated either. So great. This is an ergodic measure. Yeah? Sorry? Sorry, I don't listen. There's an alpha wrong? Sorry? Phi alpha. Ah, okay. Sure. Of course. I don't understand what you're saying, sorry. Which definition? I'm lost. What is the definition of phi alpha? Ah, okay, it's a question, sorry. Huh? Sorry. I didn't realize. There was log of alpha if you are in 0, 1/2, and log of 1 minus alpha if you are in the other one. Okay? Sorry. So great. This is an equilibrium measure which is ergodic and which supports this set. Just do Birkhoff. You'll see that it supports the set. So it's great. Question is, yeah, I'm going to finish now. Question is this the one that maximizes the supremum that we were considering? That's not a trivial question, but let me draw a picture to try to convince you. We have that. That's the pressure what we have found in terms of the variational principle is that this measure, this line here, is a tangent that passes through here. So this line is a tangent at 1. Okay? That's what we proved. So you actually have, let me point out at least, that the derivative of the pressure then is related to this here. This is the derivative of the pressure, it's the slope. It's the slope of the tangent, and it's actually related to the equilibrium measure you're actually considering. So you can think of, if you want to, as like the derivative of the pressure is in a sense the equilibrium state of the potential. So if you have two different equilibrium states, you should have two different tangent lines, and therefore the pressure should not be analytic, and you will have what is called a phase transition. Whatever. Okay, imagine that there is another measure supported on that set. So what? Oh, okay. Okay. The measure is ergodic, right? What is J of alpha? J of alpha is the set of points where the frequency of 0 is alpha, and the frequency of 1 is actually 1 minus alpha. So basically what you're saying here is that the integral of the characteristic function of 0, 1 with respect to this measure should be alpha. And the other 1/2, and here 1/2 1 should be 1 minus alpha. It's Birkhoff, right? So if you have another measure that does the same trick, then it will have the same integral, right? So any other measure, ergodic measure, that gives this set full measure has the same slope in its line, right? So it should be h nu times phi mu alpha. And because of the variational principle, this should be at most that, right? This number is constant, the lines are parallel, therefore the entropy, which is something that you can see somewhere, is large, right? What I'm saying then is that that strange number that I put at the beginning, the supremum of the entropy of all ergodic measures supporting the set J alpha, is actually this number. I'll finish the theorem next class. Well, but there's not much else to do. We already did the hard part. Thank you. Well, Lebesgue measure 1 has the dimension 1. It's a straight line. It's less interesting. The measure of maximal entropy is the same measure that passes through 1. So you only have one measure. All the measures, the equilibrium measures for t times the potential are exactly the same. You have a straight line. It's less interesting from this point of view, at least. Sorry, I don't listen to you, but sorry? J alpha is? I don't think so. It's dense on 0, 1. In particular, because you have this measure supporting it, and it's not a Cantor. It's dense on 0, 1. You have no gaps.